All right, let's talk about the time science completely broke. We're diving into a story that just tore up the entire rulebook. It's a tale of glowing metal, predictions of infinite energy, and one single desperate idea that accidentally cracked open a hidden reality, a world that's bizarre and lurking just beneath everything we see. This isn't just some dry physics lesson. It's the incredible story of how our universe got a whole lot weirder. So let's get into it. Now, I know what you're thinking. This looks like a final exam from a nightmare physics class. But really, this is our roadmap. Think of these questions as the exact clues that scientists followed, one after another, that led them out of a comfortable, predictable world and straight into the strange and fascinating rabbit hole of quantum physics. So, to really get what happened, you have to picture the world of physics in the late 1800s. Honestly, they were feeling pretty smug. They had classical mechanics, Newton's laws. It was this beautiful, predictable system that could describe everything from an apple falling from a tree to planets orbiting the sun. It was a perfect clockwork universe. Everything was logical, everything was certain, and it felt like they had it all figured out. And this slide right here, this sets up the whole fight. The classical view on the left, that's our everyday, common-sense world. Things are where they are, and if you know how they start, you can predict exactly where they'll end up. But the quantum view on the right, well, that's where reality starts to feel like a dream. It's a world built on probabilities, on jagged little steps, and on just plain weirdness. You see, this perfect clockwork theory started to stumble. When scientists started looking at things that were really, really small, like why atoms don't just instantly collapse, or things that were really, really hot, like the light pouring off a superheated piece of iron, the classical rules just broke. The math they were using started spitting out answers that were complete nonsense. The cracks in this perfect foundation were starting to show.
And one of the biggest cracks, the one that really blew the whole thing wide open, came from a really simple question about glowing hot things. Physicists call it blackbody radiation, and it was the one problem that, when they finally solved it, changed physics forever.
I mean, it's a question you've probably wondered about yourself, right? Why does the burner on your stove glow that deep red, then orange, and then almost white hot? It seems so basic, but finding the real answer forced a complete revolution in how we see reality. It turns out the universe's deepest secrets were hiding in the simple glow of a fire. So there were two big attempts to explain this glow. You had Wien's law, which worked beautifully for the high-frequency light, the blue and violet end of the spectrum. Then you had the Rayleigh-Jeans law, which was perfect for the low-frequency red light. But here's the problem. Neither one could explain the whole thing. It was like they each had a piece of the puzzle, but the two pieces just wouldn't fit together.
And the failure of the Rayleigh-Jeans law wasn't just a little bit wrong, it was spectacularly, hilariously wrong. Their math predicted that as you got to higher and higher light frequencies, into the ultraviolet range, any hot object should be putting out more and more energy, all the way to infinity. They called it the ultraviolet catastrophe. It basically meant your oven should be blasting you with an infinite amount of deadly radiation. Which, you've probably noticed, it doesn't. So, why not?
And that brings us to Max Planck. In the year 1900, he wasn't some young revolutionary. He was a pretty conservative physicist who was just trying to fix this really embarrassing problem in the math. He came up with what he thought was just a clever mathematical trick to get the right answer, a solution he later called an act of desperation. He had absolutely no idea he was about to lay the first brick in the foundation of quantum mechanics.
Okay, so here was his desperate, world-changing idea. What if energy isn't smooth? What if it doesn't flow like water from a tap, but instead comes in tiny, individual packets, or quanta? The staircase analogy is perfect here. In the old classical world, energy was like a ramp. You could be at any height. But in Planck's new world, energy is a staircase. You can be on step 1, or step 2, or step 3, but you can never be on step 1.5. Energy comes in chunks.
And this number right here, this is the size of one of those steps. It's Planck's constant, which we call h. It is a mind-bogglingly tiny number, but it's one of the most fundamental constants in the entire universe. You could think of it as the pixel size of reality itself. Every single energy exchange that happens anywhere happens in multiples of this one tiny number.
So how did this bizarre idea of chunky energy fix the ultraviolet catastrophe? Oh, it worked perfectly. Think about it like an energy budget. Making high-frequency light, like ultraviolet, requires a really big, expensive packet of energy. A moderately hot oven just doesn't have enough energy kicking around to afford to create one of those UV packets. So, it doesn't. The amount of UV radiation naturally drops to zero, exactly like we see in real life. Problem solved.
But here's the thing about solving a problem with an idea this radical. You don't just answer a question, you create 100 new ones. If energy is chunky, what else is? Planck had kicked the door open, and a whole new generation of physicists, including a young Albert Einstein, were about to charge right through it. And what they found was even stranger.
So, fast forward to 1924. A French physicist named Louis de Broglie had this really beautiful, almost philosophical thought. Scientists had already figured out that light, which everyone thought was a wave, could sometimes act like a tiny particle called a photon. So de Broglie, who just had this deep belief that nature ought to be symmetrical, basically said, well, if waves can act like particles, shouldn't particles, like electrons, be able to act like waves?
And this is the wild idea of matter waves. The theory is that everything, and I mean everything, has a wavelength. An electron, a baseball, you, the planet Earth, everything is also a wave. The only reason you don't notice a baseball's wavelength is because for big, heavy things, the wave is so incredibly tiny that it's impossible to detect. But for something as small as an electron, its wave-like nature is a huge part of its identity.
And this elegant little formula ties it all together. You've got lambda on the left, that's the symbol for wavelength, the world of waves. On the right, you've got p for momentum, the world of particles. And what's that little h in the middle connecting them both? It's Planck's constant again, the fundamental building block of this new quantum world. It's the bridge between these two realities.
So let's just pause for a second and appreciate how ridiculously fast all of this happened. In the 1890s, the universe is a predictable machine. By 1900, Planck drops the first hint of quantum weirdness. Just over 2 decades later, de Broglie says particles are waves, and a mere 3 years after that, experiments actually proved it. They shot electrons through a crystal and watched them bend and spread out, just like a wave. The old world was gone.
And this brings us to one of the deepest, most mind-bending questions in all of science. A particle, like a little ball, is in one specific spot. But a wave is, by its very nature, spread out. So if an electron is both at the same time, where is it really? This question completely shatters our everyday intuition and pulls us right into the wonderful, ongoing mystery that is quantum physics.